Okay, good morning everyone. So we start our class. Mm, so we last class we see these topics, but I got some pictures you can understand better. I already told that the translational along x, y, and z axis, three axes are in every point group. Okay, so if this is how it derived. First, you take the water molecule, and the translational is just an arrow put this in the y direction. Okay, so if you perform the e operation, there is no change in the vector direction. Okay, so you can put the +1. Okay, if you perform the c2 operations, the vector change the direction, so you can put -1. Okay, so like that, you perform the all symmetry operation of the element, you get the characters. Okay, so in using this character, you can find which irreducible representation that translational is have. Okay, so using these calculation only, they put the xyz in the group theory orbit group the character table. Okay, so for better understanding, I put this. And the rotational also like this, rotational along the z-axis. Okay, so this is the rotational along z-axis. If you perform the e operation, there is no change in the just to see that arrow. Okay, so that arrow is not changing. Okay, so if you perform the c2 axis also, the c2 axis also rotation along the z-axis, so there is that also there is no change in the vector. Okay, but if you cut a plane in the xz direction, the arrow direction will change. See this, the arrow is changing. Okay, so that's why you put -1. Okay, um, in yz direction, the also the rotational along this rotational vector is changing. Okay, if you imagine like rotational and put the mirror plane, imaginary plane. Okay, so group 3 is need lot of imagination. Okay, so you should imagine like rotational along the z-axis and cut the plane in xz direction, the rotation will change. Okay, that is -1. It got the irreducible representation a2. Okay, so the rotation along z-axis, the it is present in a2 irreducible representation. Okay, if you see the character table, you find this. Okay, so I already told the reducing formula. Okay, this is the reducing formula. The h is the order of the group, and x or h is the character for the particular class of the operation x, and xi or is the character of the x irreducible representation, and nx is the number of operation in the class. Okay, so I just last time I just say in words. Okay, so that's why I get these examples. This is chiral molecules and achiral molecules point group. Okay, these are the point groups are achiral, these point groups are chiral. Okay, simply you see the SN axis, don't muck up these point groups, just to see it contains SN or sigma or I. Okay, if it contains this symmetry operation, it is not chiral. Okay, and the point group which contains the dipole moments, these are allowed, symmetry allowed for dipole moment, these are not allowed for dipole moments. So and previous lecture I told how to find the dipole moments, which is allowed by symmetry or not. Okay, forbidden by symmetry. Okay, so group theory tells only that is allowed by symmetry or not. Okay, so the energy considerations will be covered in the quantum mechanics. Okay, so group theory is about symmetry. Okay, so it when there is a transition, it should both allowed by symmetry and energy. Okay, energy also should match. Okay, okay, so dipole moment also you don't need to muck up these groups, and just to see, you see the previous class, it contains center of symmetry or mirror plane perpendicular to if contains a mirror plane, there is no type of moment perpendicular to it. So you can also use that rules also, or if you want the examples, you see these groups, and you can try, if you take the molecules examples of these groups and find what are the symmetry element present, and find it is allowed, type of mode allowed or not. Okay, you should practice more. Okay, so if I can tell the all examples with the all symmetry elements, but it is not it is not useful to you. Okay, so it is not useful. Only you practice it, you understand it better, and it will be for not forget until any exam. Okay, so don't muck up this concept. It's like a cycling training, like cycling or bike or car. Okay, so you should try it again and again. Like it's like mathematics, you should try it, then only you should understand the imagine this rotational, this you should perform this operation again and again. Then only you got the imagination. Okay, so simply I just tell you the what how to imagine like that. Okay, so okay, this is the vibrational. Okay, normal modes are vibrations. Okay, so if you see there are three vibrationals are water molecules are active. Okay, so both IR and Raman active. Okay, so these are symmetric stretching, asymmetric stretching, and bend. This is bending. Okay, this is bending. Um, this is symmetric stretching. This is asymmetric stretching. Okay. Mm, okay. So if you perform you perform all the symmetry elements and find uh, which is find the characters. Okay, so if you like the previous translation and rotational. Okay, and find what are the irreducible representation it contains. Okay, so they do it in E and C2 sigma V. There is no change in the vector. Okay, so that these are plus one. Okay, so this irreducible representation A1 is all plus. Okay, and we solve which are the for point group, it is should be IR active in the XYZ vectors. Okay, like if you see Z transform as A1, so is that IR active, and Y transform as D2, and it is also IR active. Okay, we see the examples, then only you should understand better. Okay, and Raman active, you should the concept is you should change in the polarizability, and so we are looking for the x square, y square, z square, xy, and like that. These vectors, you see these vectors in character table and find which is IR active or Raman active. Okay. So I saw the characters contribution per atom. Okay. So this is for E it is 3, for C2 it is for CN group you should use the formula or use it mark up answer. Okay. 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 For Cn, this formula use, and for Sn use this formula. Okay.
Hello.
Okay. This is the contribution per atom. Okay, for E and sigma and I, it is constant. For Cn axis and Sn axis, there is a formula. Okay, 1 plus 2 cos theta 360 divided by n. Okay, and Sn minus 1 plus 2 cos theta 360 divided by n. Okay, so this is the one problem, previous year CSR question. The number of IR active vibrational modes of pyridine is. Okay, so this is how to solve a problem. Okay, so this is the pyridine. Okay, you see this is CTV point group. There is C2 and sigma V. There is no other rotational. Okay, the C2 is in the molecular plane. Okay, okay, so first you should calculate the number of unshifted atom. There are 11 atom. E is identity. Okay, so there are 11 unshifted atom, and if you do the C2, the C2 is passed through the, this is pretty. Okay, this is C2. Okay, so for doing C2, the number of unshifted atom is this hydrogen, this carbon, this nitrogen. Okay, so number of unshifted atoms is 3. Sigma V x z also, this plane is. Okay, so this is z and this is here. This is z and this is y. The x-axis perpendicular to it. Okay, so x z also cutting this c h and n. Okay, there is unshifted atoms is 3. Y z means this is the molecular plane is y z, so the unshifted atom is 11. The character per atom for E it is 3, and C2 it is for 1, minus 1, and sigma, all sigma it is 1. Okay, so we multiply 11 into 3 33, and 3 into minus 1 3. Okay, then using that reducible formula. Okay, number of so the formula is simple. First you should take the a1. Okay, number of a1. Okay, 1 by order of the group is 4. Okay, well, there are 4 symmetry elements, therefore the order of the group is 4. Okay, and then you should first take this reducible representation 33 into a. You should take the a, you first see the a also, a only. Okay, the this is the character in this is the number of class. Okay, so uh, there are 1 e. Okay, so 1 into the character in a1 is 1. Okay, so 33 into 1 into 1 plus minus 3 into 1 into 1. So here 1, this is 1. So these 3 number, the number near the group, and this number and this number, we will multiply minus 3 into 1 into 1, then 3 into 1 into 1, then 11 into 1 into 1. Okay, so if you solve this formula, you get the 11. Okay, like that number of a2, 33 into 1 into 1, and minus 3 into 1 into 1, and like that. So use this formula, you get the number of a1, number of a2, number of b1, like that. Okay, so the 3 number, the first number is this reducible representation. The second number is number of classes. Okay, number of class. Okay, the third number is this number. Okay, the character. So you take first a1, so you take a1 and e1. Okay, so like that you should just a mathematics. Okay, okay. So they calculate this is the total irreducible representation, and then you minus the translational and rotational. Okay, um, if you see the character table, they give the character table in the problem also. Okay, so you see the z x y z இதெல்லாம் translational, a1 and b1 b2, this is translational, and rotational is rx ry rz, these are rotational. Rx is b1, ry is rx is b2, ry is b1, rz is a2. Okay, so you you subtract it from total reduced representation. You subtract translational and rotational, you got the vibrational. Okay, so these are the vibrationals. Okay, since A2 is not IR active, so you see there is no, you see we already told that the x y z are the IR active. Okay, so A2 there is no x, there is no y. Okay, so it is IR inactive, so you should just neglect the A2, neglect A2, 3 A2 neglect. So and add 10 plus 5 plus 9 is equal to 10, 19, 24, 24. The answer is 24. Okay, so the answer is 24. So this is the formula. Okay, then this is the concept for Raman active also. So for Raman active, you see the x square, y square like that. Okay, binary system. So the Mulligan notation. So we already the previous video we told out. Okay, so how to differentiate different Mulligan symbols. Here you see the sigma h is -1, means double prime. So A2 double prime is the answer. Okay, so yeah, so don't see from first to last. So from last to, you just see how to differentiate all these. You see all are prime. This is only double prime. Okay, so it should be sigma h is -1 means double prime. Okay, so and this is examples. Okay, so it contains C4 and 2C2 perpendicular to it. Okay, so it comes under the D2D point group. Okay, no, this is not C2 D2D. There is no C4. Okay, this is wrong. Okay, okay, it is D2D. Okay, there is C2 180-degree rotation. Okay, so there is no C4. C4 means it should be 90-degree rotation. So there is, it is wrong. So it is C2 and perpendicular to 2C2. Okay, so means C2 perpendicular to 2C2 and D2. Okay, D2 and there is mirror plane also. There is no mirror plane. Okay, so sigma D is wrong. Okay, C2 is wrong. This is S4 point group. Okay, C2 and perpendicular mirror plane. Okay, so this is S4. S4 is correct answer. Okay, S4 means C4 and perpendicular to mirror plane sigma. Okay, so if you rotate 90-degree, this x come to here, then you insect a plane perpendicular to the C2 and above Cx going below. Okay, so then only you get the same structure. So it is S4 point group. Okay, so okay, so this is we saw. Okay, how to convey how to find a transition is allowed by X polarized light. Okay, so we saw. Okay, This is how to find cannot be polar if the molecule is possesses the center of inversion and cannot be perpendicular to mirror plane, cannot be perpendicular to C2 axis. Okay, molecular orbitality. So we saw the molecular orbital. So first you should find the structure of the complex. Okay, this complex structure is octahedral. Okay, so you take the octahedral point group. Okay, the we already told that the p orbital is like x. Okay, this is p orbital. Okay, this is plus and below is minus. Okay, it is like an arrow. Okay, so the xyz are the px py pz orbitals. Okay, so these you go straight in the you see in the character table, you see it is t1u. Okay, like that s orbital is a1g, it is totally symmetric. Okay, so always the s orbital is the first symmetry element, that is totally symmetric asymmetry element. Okay, and you see the d orbital, the xy dxy dyz dzx and dx square minus y square and dz square, these are all d orbital. So you see these are come into two categories, the xy yz dzx are come to the um, e these are T2G, three orbitals. So okay, triply degenerate. Okay, so means three orbitals are same energy. Okay, and EG, two orbitals. The other two orbitals are EG. Okay, these are other two orbitals. 2x square minus 2z square minus x square minus y square is equal to tz square. Okay. Um. Okay. So these are the metal orbitals. So metal ligand orbital. So just to see the metal what are the orbitals available. This is the topmost orbitals available for the bonding. Okay, so if we it is 3D for Fe 3D 6 for us to there is no 4p. Okay, but it should involve in the bonding. Okay, then only. So for only sigma only orbital, example as H2 as example. So you take all the ligands as positive. Okay, so 6 orbital is positive and do the symmetry operations. Okay, when you do the symmetry operations, it gives the first you should do the e symmetry operation. The all six orbitals are not changed, so it is 6. Okay, then you do the c3 symmetry operation. C3s are like this, the one of the other possible term of octahedral is like that. This is how looks octahedral. Okay, so c3 is like this. So if you perform the c3 axis, all orbitals are change their position. Okay, so 0 and we see the unshifted, okay, atoms or molecules. So you just need the symmetry. Okay, so you just to put the plus. Okay, so because all H2 are same. Okay, so that's why we just need the symmetry, not the whole orbital or whole molecule. Okay, don't need the H2O full H2O molecule, you just need the symmetry. Okay, so that's why what are the unshifted and C2s are perpendicular to this. If it is octahedral like this, the you see it is also 6 C2s are not go in the bond axis. Okay, the 3 C2s only go with the bond. Okay, so you find this irreducible operation characters and you reduce it using the reducing formula, you get the ligand orbital. So these are the ligand orbitals. Okay, so then compare. So there are no orbitals with the T2G here. Okay, so metal orbitals A1G here A1G, T1U here T1U, EG here EG, but there is no T2G orbital. So the T2G orbital of the metal is non-bonding. Okay, the you see this is the molecular orbital, these are the ligand orbital and these are the metal orbital. So the you see the T2G orbitals are non-bonding. Okay, so this is the delta O difference between T2G and EG. Okay, So when the pi ligands are involved, so pi ligands are perpendicular to the sigma bonds. Okay, so these are the two pi bonds. Okay, so for represent this, you should use the two arrows. So we here is these are the two arrows. So the same principle. Okay, if you should only consider the unshifted. Okay, so if the direction of the arrow is not changed, it is plus. Okay, for E, the whole 12 arrows are unchanged, and the direction also not changed, so it is 12. Okay, for C3, all are changed. 6C2 also changed. 6C4 also changed. For 3C2s are this is that 3C2s are going like this, the bond. Okay, so if you do these operations, um, the four arrows in the two bonds are change their direction. Okay, so that's why -4, and the other all symmetry operation it is 0. Okay, so if you reduce this reducible representation using the reducing formula, you get the uh, pi ligands reducible representation. Okay, so you see the pi bonding. um, Here T2G orbital is only pi bond. This only uh, overlap with the non-bonding metal 2 orbital. Okay, so because the T1 is non-bonding, because metal T1U orbitals are already involved in sigma bonding. Okay, so it cannot be involved in bonding. And T1G and T2U, these also there is no symmetry with metal orbital, so these are also non-bonding. Okay, so only the T2G orbital only bonding. Okay, the others are non-bonding. Okay, T1U there is symmetry with the metal orbital. Metal orbital also contain T1U, but it involve sigma bonding. Okay, so it cannot be involved in pi bonding. Okay, you see this is the T2G orbital using pi ligand. So the same ligand can use act as a pi donor or pi acceptor. Okay, so but here there are two concepts. One, uh, pi negative pi ligands. Okay, so Cl minus like that. So these ligands are slightly more electronegative than metal. Okay, so their T2G orbitals are slightly lower energy than metal T2G orbital energy level. Okay, so if these two orbitals coupled, you get two orbital T2G and T2G star. Okay, you see, first, if it is non-bonding means this T2G is in between this. So there is the T delta O is uh, delta O is decreased from sigma only to pi bonding, pi donor ligands. Okay, so this is the reason for strong ligand. You see, some ligands are weak, some ligands are strong. When there is a strong ligand, you say the pairing will undergo. Okay, so like these concepts are related with these energy levels and symmetry. Okay. Okay, and some ligands are pi acceptor ligands. CO like pi acceptor ligands are slightly higher energy than metal D2G orbital. So here also, here the delta O is higher than the normal T2G only. So if it T2G is non-bonding, the del O is small. Okay, so if it is pi CO like pi acceptor ligands, the T2G is this del O is larger than the normal del O. Okay, sigma only del O. Okay, but the previous case, this is del O is smaller than the sigma only del O. Okay, okay. So you should study this concept. This is the spectrum look like. Okay. I already told that group theory is like mathematics. There are not one way. There is no many other ways to calculate group theory characters and the IR active and Raman active modes. So there are many ways. You studied different ways. Okay, so which concept is you familiar? You follow that concept. Okay. Uh, so you cannot say this is the correct and this is not correct like that. So all are correct. Mathematics, you can use many different ways to find a same answer. Okay, so don't confuse with other concept. um, so always follow one concept. Okay, so if you follow my concept, you follow this. Otherwise you follow your own concept. Okay, you whatever what concept you studied. Okay, you all know G into G, Jared into Jared J, direct product determination. So it will be useful for I told you. This is how to find a selection tool for spectroscopy. Okay, so you find the first molecules and molecular point group and geometry to point group and point group to character table. From character table, you can determine the symmetry of the molecule motion, determine the symmetries of molecular orbital, and determine the interactions of equivalent nuclei. Okay, uh, character table 2 you can find the this is the direct product table, so it will be useful in the allowed IR. So you saw the previous questions, it is allowed by IR x polarized light like that. Okay, so we saw the example. Okay, so this is the formula. It is from quantum mechanics. Okay, so the intensity is proportional to the square of the transition dipole moment. Okay, this is the transition dipole moment. The transition dipole moment is directly proportional to the this equations. Okay, this don't confuse with this. This is initial, this is final, this is dipole moment vector. Okay, so this dipole moment vector is determined which is x polarized or y polarized or z polarized like that. Okay, this is initial, the transition from ground state to accelerated state. This is ground state to accelerated state or accelerated state to ground state. All these transition. The transition is only allowed if it contains the totally symmetric irreducible representation. Means A1 or A1G or A1E like that. The first character in the character table. Okay, so if you got this only, the transition is uh, it is symmetrically allowed. If it does not contain totally symmetric, it is forbidden by symmetry. Okay, so we saw example, you will understand better. Okay. So we talk a particle in a box. We take an example particle in a box from AG to AU. Okay, so transition between AG to AU. This is CA point group. Okay, so you saw this video on YouTube. I put this link in description. You saw the full video. Okay, so you can understand better than I can explain. Okay. So simply the first ground state to excited state is allowed or not. The ground state is AG and the excited state is AU and the X polarized light is symmetry is AU. Okay, so you put AG into AU into AU. Okay, so the direct product table is simple. First you multiply AG into I am already told that group theory. You multiply from right to left. First AG into AU, AG into AU, you got the AU. Okay, so you put the AG into AU is equal to AU, and AU into AU, AU into AU equal to AG. Okay, so AU into AG, AG. So if you got the AG, uh, this is not equal to 0 means it is allowed transition. Okay, so AG to AU is allowed transition. So okay, then only we say G to U transition is allowed, U to G transition is allowed, but G to G and U to U are forbidden. Okay, So this is the formula how it come from. Okay, so you should know the symmetry of the ground state and the symmetry of the excited state and symmetry of the light. Okay, so we use the light, so you excite a molecule, photons, you use photons. Okay, so that photon should contain some symmetry. Okay, so that is x polarized light, y polarized light. That symmetry, so this is we calculate symmetry allowed. Okay, so this symmetry should be allowed. Multiply all these values, you get totally symmetric irreducible, means it is allowed to by symmetric. Okay, so otherwise this transition is not allowed by symmetric. Okay, okay. So Raman also the same effort. For what is difference between absorption and scattering? Absorption is the energy level should match the incoming light's energy level. Okay, so it match, it absorb. If it what the difference between the Raman is scattering, means the light is not absorbed. It go into the molecule and scattered back. Okay, so this is the virtual energy level. Okay, means the light's energy is not matched with the energy of the molecule. Okay, so it may be rotational or vibrational, anything like that. So then scattered back. Okay, so what is the difference between there are three different scattering. Okay, Rayleigh scattering, Stokes and Stokes. Rayleigh means the photon's energy is not to decrease or increase. Means elastic scattering, same undergoes the same, it is Rayleigh scattering. If it somehow loses energy and go to the this you see the incoming light's energy is higher than the scattered light. So you see the arrow is small, means the energy level, these are energy level. Okay, so these are energy level. So the energy is somehow lost, the photon is somehow lost the energy, and it take the molecule from Ag to Au. Okay, it may be rotational or vibrational, anything like that. If it molecule in the ground state rotational level, it take the molecule to the first excited state of the ground molecule. So this transition is allowed or not. So you see the selection rules. This is +1, -1, delta J +1, delta J -1, like that. Though these all selection rules come from these concepts. Okay. Okay. So see the simple. Okay. So first here we take the character table. Okay, and you see the scattered use x square orbital. Okay, so this is the light's symmetry. Okay, so x square for Ag. Okay, and ground state is Ag, and x square is Ag, and excited state is Au. Ag into Ag, Ag, Ag into Au, Au. Au means it is equal to 0, means not allowed. Okay, so that's why they for scattering the all transition is +1 +2 like that. Okay, for delta J rotational energy is +2. Okay, plus or -2. Okay, +2 means Stokes, -2 means anti-Stokes. Okay, okay. This is the Rayleigh scattering, means 0, Raman scattering 0 2 or Raman scattering. Okay, sorry. Okay, uh, this is for understanding, better understanding. Okay, so you don't need to muck up all these things, just understand what is why, how it is symmetrical allowed. The symmetry of the ground state and the symmetry of the excited state and the symmetry of the light used. Okay, for excitation or scattering we use the light. Okay, so light is electromagnetic wave. So this it also contains some sort of symmetry. Okay, so this is plain polarized lights. Okay, X polarized, Y polarized, or plain polarized, means the lights are so normally the light from our tube lights like that are multi-directional. So these lights are polarized to only one direction, means the light only come from X polarized lights, mean the direction of the light is X only. Okay, so okay, so we saw homo to lumo transition. The homo, they give the homo energy level, lumo energy level. Okay, normally all alkyne butadiene, like that, you these kind of examples they give the ground state symmetry and the excited state symmetry, they give the point group, and they ask the question which is allowed by which polarized light, X polarized light or Y polarized light or Z polarized light. Okay, you should know the character table, or you should know, if you don't know the character table, you should familiar with this concept. Anything you multiply with a1 means other totally symmetric means you got the same b into a1, you got the b, okay. And any element it's multiplied by twice b into b, b1 into, okay, b1, take b1 into b1 equal to, we get the totally symmetric. So using these two rules you can find the, okay, for you take a1 into a1 means a1, a1 into a1 a1, so it is allowed by z polarized light, okay. If it is xy polarized it means e, okay, a1 into e means e, okay, e into a1 equal to e, okay. You multiply anything with a1 is like you a1 is like it is you it is from mathematics, okay. So a1 is like um identity or identity matrix, okay. So the character is like 1 0 0 0 1 0 0 0 1. So if you multiply any matrix with this matrix, you get the same matrix any number. So you know the matrix multiplication, okay. So multiply this, you get the same. So that's the formula. You multiply any irreducible representation with a1, this is the a1, okay. A1 or a1g or anything like that, totally symmetric, okay. So multiplies the same will be you obtain. So and any this you multiply twice, you get the a1, okay. So these are from matrix multiplication. First first the characters the character tables are all from the matrix calculations, okay. So you don't need the matrix calculations, you should just understand this concept, okay. Then you can easily solve. So here we take the examples, okay. Homo is a1 and light is e, and light e means what it means. E means it is x comma y in e irreducible representation, okay. That's why a1 into e means e, okay. It is unchanged, and e into a1 is e, okay. So it is xy is not polarized, z is polarized, okay. Okay, these questions are asked many times, okay, in csir and gate also. These are the rotational energy levels, pj into j plus 1, okay. It will be any energy level, okay, rotational, vibrational, anything like that. So you should know the ground state energy level, excited energy level, and the light energy level, not energy level, ground state symmetry, excited symmetry, and light symmetry, okay. Okay, so the same concept for rotational modes. Y rotation. So here we take the y rotation, okay. The ground state is a1, y is b1. So see, take the screenshot and you solve these problems, okay, by yourself. Then only you understand better, okay. Vibrationals also same formula. So here the asymmetric stretching is B2 symmetric, okay. So ground state is A1, okay. Ground state is A1, and the excited state is after sketching it is become B2, okay. Before sketching it is A1, after sketching it is B2, okay. If it is allowed by y polarized light but not z polarized light, okay. The y polarized light symmetry is B2. So you put B2, A1 into B2 is equal to B2, B2 into B2 is equal to A1. I told already, if you multiply same you get the A1, okay. A1 same A1 or B1 B2 anything multiply twice it get the same A1, okay. So that is the orthogonality. See some, if you know the great orthogonality theorem, you find why it is like that A1, okay. If you really want you curious about the answers, you find search yourself, okay. This is the Laporte selection rule. G into G, U into U forbidden. See, G into G U forbidden, G into U and U G are allowed. So I explain how these formulas are. Most of them knows these formulas, but don't know how they come from. Okay. Okay. Spin selection rule. In the spin, there is a difference. Okay. So the spin is not in dipole moment operator. The dipole moment operator does not interact with the spin. So for spin, you need the ground state and excited state symmetry only. You don't need the light's energy level. Okay. So I already did it. So from this vector only determine the spin transition is allowed or not. You see here is ground state and excited state. So you just see the ground state symmetry and excited state. If both are A1, you give the A1. It is allowed. I already told that both is same B2 into B2. You get the same symmetry. Okay, A1. So A1, if you get the A1 means it is symmetrically allowed. Okay, so you saw the examples. Okay, here, example. Okay, so formaldehyde. Okay, you take the formaldehyde and ground state electronic configuration. You write the ground state electronic configuration, and this is the ground state electronic configuration. And this pi to pi transition, it is allowed by spin allowed or not. Okay, you see, this is the pi orbital, this is the pi star orbital. So you see the pi orbital symmetry is B2, pi star orbital symmetry is B2. Okay. If you transition is pi to pi star transition, so the orbital is going from B1 to B2. Okay. So means ground state symmetry is B2, the excited state symmetry is also B2. Okay. You multiply B2 into B2, you get the A1. Okay. A1 means you get to A1 means it is allowed by symmetry. Okay. A1 means allowed by symmetry. Okay. So concept is simple. You all know the ground state also excited state should means singlet. Okay. So if ground state is singlet, excited state should also singlet. Ground state is triplet and the excited state also is triplet. Okay. Because if it change the direction, they change the symmetry. Okay, so the symmetry will be changed. Okay, the symmetry should not change. So if it is paired and excited to unpaired, okay, become unpaired, but it should not change the direction. Okay, you see, this is this direction and this is this direction. So if it the spin of the two electron excited must be opposite. Okay, means why the spin must be opposite? Means this is singlet. Okay, you know, this is also singlet. Okay, this is half, this is minus half, this is half, this is minus half. Means s is 0, 2s plus 1 is 0. Okay, I mean singlet. Means the symmetry is not changed. We all know singular to singular transition is allowed, singular to triplet transition forbidden. The you see the this is multiplicity. Spin not spin, this is spin multiplicity. Okay, so some transition are allowed or not, we just see the spin multiplicity which is allowed or not. Okay, the real concept behind is symmetry. The symmetry of the electron should not change, should not change. If it is changed means the it is not allowed, forbidden by symmetry. Okay, you see this 4 mark question. B1 U2 B2 transition in ethylene is allowed or not. So the using the problem solving is really simple. Okay, you understand the concept is the very important. You take the b1u characters and write it, and take the p2g characters, here b2g character, and write it. Just to multiply it, what element you get? You see, you get the 3 b3u. It is x polarized, it is allowed by x polarized light. Okay, so how it is come from? Okay, simple. So first, the formula is like that: ground state, the polar x polarized light, and excited state. Okay, The ground state is we first multiplied b1u and x polarized light and y polarized and excited state. This is the concept, but you don't need to go with this concept. Okay, so if you multiply this, you get means first is a1g b1u, you multiply with uh, b2g. Okay, we get to b3u. Okay, so the excited state should all this is the reverse calculation. Okay, reverse calculation. So if you get this c3u, then it should be x polarized, then only you get the a1. Okay, so the calculation is simple, just to multiply it and find the characters we match with this irreducible representation, which is y x allowed. But the real concept is this is the real concept. Okay, the ground state, excited state, and the ground state symmetry and excited symmetry and the light symmetry should if you multiply these three, you get the a1. Okay, this a1. Okay, then only it is allowed by that light. Okay, this is the concept. This is a famous video, okay, YouTube, but they don't tell the concepts. Okay, this question also from H2O, the electronic transition from ground state to excited state B1 symmetries. The ground state is A1 and the excited state is B1. Just multiply these two, you get if you multiply A1 with B1, you get the B1. Okay, so you see the B1 x polarized, so it is allowed by x polarized, right? Okay, so simple. The problem is simple, but this is one problem. Okay, so if you see this is in YouTube, just pause the video and find your answer by yourself, then check with the answer. Okay, this is gate 2020 this year questions. Okay, so how to solve this question? Simple. Okay, here a point is originally at 1 comma 3 comma 5 subject to a symmetry operation that shifted the point to -1 -3 -5. Subsequently the point at -1 -3 was subject to another symmetry operation that shifted the point to -1 -3 -5. The symmetry operators are respectively. So first you should take this example. Okay, so this is one of the method. I already told you there are many methods to solve a problem. Okay, this is all mathematical problem. This is one of the my method, so I think it is very easy. Okay, so you see xy is at 1 1 1 plus 1 plus 1 plus 1. You just see the sign. Okay, these are all plus. Okay, means they after the symmetry operation they all shifted to -1 -3 -5. Okay, means the x and y are changed, z is not changed. Okay, the 1 comma 3 comma 5, take this is x, this is y, this is z. After the symmetry operation 1, you get the -1 -3 minus plus 5, means the x and y are changed but the z is not changed. What are the symmetries you can do? Okay, uh, first you take the c2x. Okay, c2x means the rotational about 180 degree along the c2 x-axis. Okay, x-axis. If you rotate along the x-axis, the y and z are changed their position to the negative. Z become minus z, y become minus z, minus y. Okay, so this is not the answer. And c2z means if you rotate along the z-axis, the z is not changed, but x is going to minus x and y is going to minus y. So this is the answer, minus x minus y. Means the answer is c2z. Then another operation is shifted the -1 -3. You take this already you did the operation, you should take another operation which change the x and y signs are not changed, z only changed, -5. Means the x is that sigma x is plane in the xy direction. If you insert a plane in xy direction, the z plus z become minus z. Okay, so this is the plane. So if you insert a plane in xy plane, the plus z become minus z. So This is the answer, and this is these two symmetry operation. Okay, you check the answer by yourself. Okay, and this, you find what point group this is. This is differ 2016. I take only the standard questions. Okay. And this is original website's question, so there is no mistakes. So always questions from original TIFR or gate questions. You can get the gate question from the gate websites. Okay, so don't take the question from coaching center like that. So there are many mistakes. So if you are familiar with the concept or you have the book, you can check it is correct or not. If you don't have this, you should don't make mistakes. Okay, you find that this is a water cluster. Okay, so not a single molecule, water cluster structure. Okay, so find the point group. You see the different questions are like these standard questions. So find the pause the video and find the answer and check the answer. Okay, this is IR active or Raman active. Okay, so I there is no slide now, I think. So this is the tetrahedral molecule A1 vibrational mode correspond to all the mx bonds stretched the same distance simultaneously. With which spectroscopy technique is this vibrational mode observable? uh, so you find the answer by yourself, so it will be interesting. Okay, so I know the answer. Okay, thank you.